Hello viewers, welcome back once again to my channel Math Made Easy with PDY. I would like to use this opportunity to thank you for the support given me on this channel. It's a great privilege always coming your way with new videos. If today is your first time watching this video, I would like you to kindly subscribe to my channel and then also share the videos with other friends so that together we can make math easy to study. Without wasting my time, today we are going to look at the topic differentiation. In other words, we say it is known as derivative of a function or derived function. But on this topic, as broad as it is, we are going to break it into various segments. Hence, we are going to take the subtopic derivative of functions from first principle. When we talk about differentiation, someone may ask, what exactly is differentiation? Differentiation or differential calculus is simply the branch of mathematics measuring rate of change. Differentiation or differential calculus is a branch of mathematics measuring rate of change. So you can look at this word here, rate of change. Rate of change, meaning there's a change in quantity from one state to the other. The word differentiation looks so big, but let me break it down into simple understanding. From our basic studies of a straight line, we found out that we learned something concerning the gradient of a line. So if I have my Cartesian plane shown as this, and I do have a straight line on it, there are different points on this straight line, different points on the straight line, different points. But you realize that the different points, as we see, they have corresponding x values and they are corresponding y values. So if I have x1 here, y1 will be there. So let's take this line to be known as f of x, or you can actually say that it is y. Likewise, you may have x2 here and its corresponding y2 be there, or you can say it is x2 going with f of x2 or x1 going with f of x1. Then we may have equally x3 here and the corresponding y3. Likewise, x4 will have its corresponding y4 or f of y4. Going further, you realize that when you are finding the gradient on this line from coordinate geometry 1, you find out that getting the gradient on the line, you need to select 2 points on the line. And therefore, selecting 2 points on the line, we can say that if we have the coordinate of x4 and then y4 and that of probably x1 and then y1 to be my coordinate, then I need to find the rate of change with respect to the x component as well as the rate of change with respect to the y component. So that is going to give us, if we should form a right angle triangle, then it means we are going to obtain change in y component and then change in x component. So the change in y component actually gives us what we call y4 minus y1. And then change in x component will be giving us x4 minus x1. So that's the whole idea. Therefore, gradient on the line, which we say m, is equal to the rise over run. And that will be giving me m equal to y4 minus y1 all on x4 minus x1. And interestingly, gradient on a line is fixed for all set of points on that given line. But the question now is, does the idea of gradient of a line the same on gradient on curves? Because when we talk about differentiation, then we are looking at the general function altogether. You know, we have different types of functions altogether. A straight line can be a function, a curve can be a function, and it goes on and on and on. Therefore, differentiation talks about the general gradient on a given function. Differentiation talks about the general gradient on a given function. But the idea of gradient on a line cannot be used on the gradient on a curve. Therefore, how do we move further to generalize how to get the gradient on a curve? Now, why do we say that the gradient on a curve differs? Let's take it that we have another Cartesian plane drawn here. And with this Cartesian plane, we have my y-axis here. I have my x-axis there. Now, on this Cartesian plane, I have what we call a curve. You bear with me that if I have set of points on this curve, I have different set of points on the curve, as I'm showing. So probably we have x1 here, corresponding value for y1 will be there. I may have x2 here, and when I trace it to the side, then corresponding value for y2 will be there. Then it goes on and on. x3, corresponding value for y3 will be found there, and it goes on and on and on. Now the gradient of this curve will differ from one point to the other. And a perfect example I will always like to use to explain that the gradient on curves differ from one point to the other is simply just consider a car moving at a very top speed in a straight path. You realize that it goes with a constant acceleration. But when it gets to the curve, you realize that it needs to slow down so that it can give or it can take a very smooth turn. If not, accidents may just simply take place. So gradient on curves changes from one state to the other. But gradient on straight lines are constant. So as I said, differentiation is all about finding the gradient of a function at a given point on the function. So let us see how best we can use the idea of gradient of a line to determine the gradient of a curve at a given point. So to determine the gradient of the curve at a given point, let's consider our curve on this Cartesian plane. And then let's have a curve which shows some coordinates on it. So probably let's take it that we have the coordinates x. The whole curve is actually known as f of x, and automatically it will have the corresponding value for y, which is going to be f of x. Now when I move some distances away from the point x ahead of it, whereby let me call it a distance of h. Let me call it a distance of h. Let me move h distances away to another coordinate here, which will have its intersection at a point here. So the coordinate or the point for x here will actually be x plus h, because I've just increased the distance from h to another point, and therefore that point over there will be x plus h. To get its corresponding value for y, then we just have to substitute the value of x plus h into the function, and that will give us f of x plus h. Remember, that's our y-axis, and this is our x-axis. Now, so the coordinate here is x comma f of x, and that of the coordinate here is x plus h comma f of x plus h. Joining these 2 points, which is found on a curve with a straight line, with a straight line, we may have this, because we want to use the idea of using the gradient of a straight line to determine the gradient of a curve at a given point. And in this case, if I should have actually worked on finding the gradient on this straight line, that will be giving me the gradient m will be equal to the change in y over change in x. And per the coordinate that I have there, change in y is going to be f of x plus h minus f of x. Remember, f of x plus h is the y component for this point here, and then f of x is the y component for the point here. All divided by x plus h minus x. Now when we go further and simplify, that is going to give me m is equal to f of x plus h minus f of x. All on h will be the only variable left, because x minus s will give us 0, so we'll be left with h. Actually, that is a gradient on the line, but we want to find a gradient on the curve. And in determining the gradient on the curve, then it means at a given point, then it means that we need to reduce the distance of the point or the line from this end all the way to the point x and f of x. So if I should reduce that distance, then what does it mean? It means that the h value will be approaching 0. If I should reduce the distance from the point here to there, and therefore when I do reduce it, it means that at this point the straight line over there is going to form what we call a tangent. It will form a tangent at the point, because when I reduce the distance from this edge or this point to that, it's going to form a tangent. It will not give you a straight line joining 2 points, but it will just form a tangent at that given point on the curve. and hence it means that the h value will be approaching 0. There wouldn't be any distance for h. Remember, the h was representing the increment in the s value. So if there is no value for h, then we say that h is approaching 0. And therefore, this is what we term as determining the gradient of a function at a given point using the concept of limit. And that is the first principle when it comes to differentiation. Therefore, in finding the gradient on the curve at the given point, it brings about the idea of differentiation. And the symbol now becomes limit as h approaches 0 for the gradient of the function, which is f of x plus h minus f of x all on h. And this is what we term as the derivative of the function from first principle. And the symbol for differentiation is dy dx. So dy dx is equal to limit as there's a change in the s value approaching 0 for the gradient of the function. So in other words, we are going to use the concept of first principle to find the gradient of given functions. So to begin with, let's just take some work examples. We may be asked to determine the gradient of a function from first principle having y equal to 2x plus 3. So determine dy dx from the statement here, from first principle. Now, as we said, from first principle, then what we need to bear in mind is that dy dx must be equal to the limit as h approaches 0 for f of x plus h minus f of x all divided by h. So from our function given to me, when we are asked to determine from first principle the gradient of this curve, then we can say that let f of x equal to 2x plus 3. And per the relation we've established from first principle, then we need to also know f of x plus h. So when you have a function with an increment, then it means our original function now becomes 2 into bracket x plus h, then plus 3. Wherever we see x, we substitute the value of x plus h there so that it completes the other function. Then moving further, we can substitute the expression we've had here into the first principle relation. So dy dx will be equal to limit as h approaches 0 for 2 into bracket x plus h plus 3 minus into bracket 2x plus 3 all on h. Now from the concept of limit, which we did early on, we need to simplify the expression before we do substitute the value of 0 into the function for h. Because at the moment, if you don't simplify and you substitute the value of h as 0, the whole statement becomes undefined. Hence, to simplify, we have limit as h approaches 0 for 2x plus 2h plus 3 minus 2x minus 3 all on h. Going further, we are going to obtain limit as h approaches 0 for 2x can subtract 2x here, and that gives us 0. Positive 3 also does away with negative 3, and that gives us 0. And therefore, we are left with 2h on h. Therefore, dy dx will be equal to limit as h approaches 0 for, now h will go into h, leaving just the value 2. Now you learned early on that since there is no h in the statement, now it's left with a constant. So limit of a constant as h approaches 0, it still gives us the constant 2. So it tells us that dy dx is equal to 2. Then the gradient of the function y equal to 2x plus 3, actually the gradient is 2. And it actually confirms that when we go back to our coordinate geometry 1, whereby we learned that the standard form for every equation of a line given as y equal to mx plus c, when you compare, it tells you that m is equal to 2. M is equal to 2. So from first principle, we've actually also established that the gradient on a line is actually constant. And per the first example we've taken, we've seen that the gradient is 2. Let's take another example. Now, considering another example, we may have, from first principle, determine the gradient of the function f of x equal to x squared. We are to determine the gradient of this function, x squared. Now, if you analyze it carefully, you realize that this function is a quadratic function. And therefore, when you sketch the curve, or when you sketch the graph of it, you obtain a curve. So you learned that the gradients on curves differ from one state to the other. It tells you that when we find the gradient of this, we are not going to obtain a number or a constant as we did it for the straight line. Therefore, from first principle, we know that the gradient dy dx is equal to the limit as h approaches 0 for f of x plus h minus f of x, all on h. So we already have f of x. So what we need to establish is the small change in x. So f of x plus h. And that will be given as, just substitute the expression of x plus h into the function. So we have x plus h all squared. Now we can simplify it before we go to substitute, and that will give us s squared plus 2xh or 2hx then plus h squared. So substituting these two functions into a relation for first principle, then dy dx will be equal to limit as h approaches 0 for s squared plus 2hx plus h squared minus x squared, all on h. Simplifying the numerator, that will give us limit as h approaches 0 for s squared minus s squared will give us 0. So we are left with 2hx plus h squared, all on h. At this moment, we cannot substitute the value of 0 into the function because it will give us an undefined solution. So we need to remove the discontinuity from it, which is the h. So we can actually factorize out. So we have limit as h approaches 0 for h out into bracket 2x plus h, all on h. Remember, h was common to the numerator, so h was out, and h multiplies 2s to give us 2xh, and then h multiplies h to give us h squared. That's why the h was factorized out. Now this 2h, h will go into itself 1 and go into the denominator also 1. So we are going to be left with dy dx will be equal to limit as h approaches 0 for 2x plus h. At the moment, when you substitute the value of 0 into the function, you will not get an undefined solution. So we can go further and say that therefore 2x plus 0 will give us dy dx. And we have the final answer as 2x. So it tells you that gradient on the curve x squared will be established as 2x, meaning whatever value of x when substituted into this expression tells you the corresponding gradient automatically. It tells you the corresponding gradient automatically. So that is another way you can actually find the gradient on a curve at a given point. But remember, we are using first principle to determine that. I've taken the first two examples as polynomial functions. Let me take one other example with respect to function under the radical sign. Function under the radical sign. So let's consider having f of x given as square root of x. We are to determine the gradient from first principle. We are to determine the gradient from first principle. So you bear with me that f of x equal to square root of x can also be written as f of x equal to x to the power half. So take note of that. But I'm not going to use it today. I'll use it another time. So from first principle, we've learned that then dy dx must be equal to the limit as h approaches 0 for f of x plus h minus f of x all on h. And therefore, we need to find our f of x plus h based on what we've been given. So finding f of x plus h, we need to have it as square root of x plus h. I believe it's well understood. So let's substitute the expressions in there. Dy dx will then be equal to limit as h approaches 0 for f of x plus h has been found to be square root of x plus h. Then minus f of x, which is square root of x, all on h. All on h. Remember again, from limits of sets, you cannot substitute directly because you are going to end up getting 0 over 0. How come? When you substitute 0 in place of h, then it means you are going to get square root of x minus square root of x, which is 0. And when you replace h also with 0, so you are going to get 0 over 0. And 0 over 0 is undefined. Therefore, how do you work it out? Now, in order to solve such a question, then we need to rationalize. We need to rationalize. So we are going to have limits as h approaches 0 for square root of x plus h minus square root of x. When you are rationalizing the numerator, then it means you have to multiply it by the conjugate of it. So that is going to give us multiplying square root of x plus h plus square root of x all on h multiplying square root of x plus h plus square root of x. I believe you've understood how I had to rationalize. Now, going further, we are still having limits as h approaches 0 for the numerator becomes difference of two squares. So that is going to give us square root of x plus h all squared minus square root of x all squared, all divided by h into bracket square root of x plus h plus square root of x. I hope it is clear. Now, in simplifying, we are going to have dy dx equal to limit as h approaches 0 for x plus h minus x all on h into bracket square root of x plus h plus square root of x. Now, the numerator will be simplified, so we have limit as h approaches 0, leaving h on h into bracket square root of x plus h plus square root of x. And therefore, since it's in the factor form, h will do away with the h here, leaving 1 for the numerator, and then we are left with limit as h approaches 0 for 1 over square root of x plus h plus square root of x. Now, at this moment, you realize that we have to ask ourselves basic question. When we substitute the value of 0 into the function, will it give us an undefined solution or not? And ideally, it's not going to give us an undefined solution. So therefore, we can go ahead and substitute. So we'll have it as 1 over square root of x plus 0 plus square root of x. And that'll be left with 1 all over square root of x plus square root of x. And when you have the addition of two sets with the same radicand, then we need to add up the coefficients. So that is going to give us 1 over 2 root of x. So that tells us that when you find dy dx, or when you find the gradient of square root of x, you end up getting 1 over 2 root of x. So I've taken one example of a surd, a function which is a surd. So let me take another example. Remember, the more examples you work it out, the easier it becomes. So kindly do more work example. I can give you more work example on that. So let me take another type of example whereby it involves rational functions. So another example involving rational functions, we may have find the derivative from first principle for the function f of x equal to 1 over x. So we are finding from first principle. So we need to find actually f of x plus h. And that will give us 1 over x plus h. So we need to work out that. So from first principle, then we know that dy dx must be equal to the limit as h approaches 0 for f of x plus h minus f of x all on h. Going further, then I just have to substitute my values of f of x and f of x plus h. So that will be leading me to limit as h approaches 0 for 1 over x plus h minus 1 over x all on h. Now, because it's function over another function, let me try and write it in a very simplified form for better understanding. This is the same as limit as h approaches 0 for 1 over x plus h minus 1 over x, all dividing h. And remember, the division sign can be changed into multiplication, so we are going to end up getting it as limit as h approaches 0 for, now let's simplify what is here. We'll find the LCM. The LCM is going to give us x plus h multiplying x. Therefore, x plus h goes into the LCM x times, multiplying the numerator, we'll end up getting x. Then minus x goes into the LCM, we'll get x plus h, multiplying 1, so we have into brackets x plus h. Then remember, the division sign we have here can be changed into multiplication, so it becomes times, then we find the reciprocal of the h, so that will be 1 on h. So going further, then we have dy dx is equal to limits as h approaches 0 for, now we have x minus x, that will give me 0, leaving negative h, multiplying 1, that will give us negative h. But the denominator is going to be h into bracket x plus h times x. I believe it's well understood. Now, the numerator was left with h because we had x minus x giving us 0, and the negative sign affects the h, so we still have negative h. Multiplying 1, we still have negative h, and that's what we have here. And then when we multiply the denominator, we'll have h multiplying h plus x, then times another x. I didn't actually expand for the fact that when it's in the factor form, it is easier to do away with common factors. That's why I never expanded. So I would advise you not to be expanding. Just always write your expressions in the factor form so that you know which type of variables to do away with. So in this case, you realize that the h will go into itself 1 and go into the h here 1. So you're left with negative 1 for the numerator. So we'll have limits as h approaches 0 for negative 1 all on x plus h multiplying x. That's what we have left. And going further, then at this moment, we can go ahead and substitute the value of h into the function. So we have negative 1 on x plus 0 all multiplying x. And that will be left with negative 1 all on x squared. So it means that the derivative of 1 over x is actually giving us negative 1 over x squared. dy dx is equal to negative 1 over x squared for that. I believe it is well understood. So far, so good. I've been able to take as many work examples on first derivative for functions, and I've explained what the concept of first derivative is all about. Now let's go further and see how best we can solve these questions from our WASSCE examples. Now we have some work examples here. It says this question came in the year 2018. It was an object question. Find from first principle the derivative of y equal to x squared plus 1 with respect to x. So we can say that then f of x is equal to x squared plus 1. And we need to know our f of x plus h. So f of x plus h must be equal to x plus h all squared, then plus 1. Now let me simplify this expression before I do my substitution. So that is going to give me x squared plus 2xh plus h squared then plus 1. This is what I have. Then from first principle, then we have to state that then dy dx should be equal to limits as h approaches 0 for f of x plus h minus f of x all on h. So our substitution then can be made, and we'll have it as limits as h approaches 0 for x squared plus 2xh plus h squared plus 1 minus s squared plus 1 in brackets. Remember, it's a binomial expression, therefore you have to put it in brackets, all divided by h. Going further with simplification, we have limit as h approaches 0. The numerator is going to be left with just some few expressions, because the s squared over here, when we expand the negative sign through, it will give us negative s squared. So we'll have it as s squared minus s squared. I'm regrouping at the same time. And then I also have plus 2xh plus h squared plus 1 and then minus 1. So I've actually done two things at the same time. I've expanded, simplified, and regrouped so that like terms can be done away with. Then we have all divided by h. Going further, we have dy dx equal to limits as h approaches 0. For the numerator, we'll be left with 2x plus 8, 2xh plus h squared all on h. Then at this moment, as you know, we cannot substitute the value of 0 into the function because it will make it undefined. Therefore, we need to factorize out to remove all discontinuities. So limit as h approaches 0 for h out, 2x plus h all on h. So the h for numerator and denominator will be cancelled out, and it will be left with limits as h approaches 0 for 2x plus h. At the moment, we can go ahead and substitute the value of 0 for h. So we have it as 2x plus 0, and then we have it as 2x. Therefore, dy dx is 2x. dy dx is 2x. And that finds from first principle the derivative of y equal to s squared plus 1 with respect to x. Another example is this. Find from first principle the derivative of this. F such that x maps to 3x squared plus 4x. So as you know, then we have f of x given as 3x squared plus 4x. So we need to find f of what? X plus h. And that should give us 3, wherever we see x, we substitute x plus h there. So we have 3 into brackets, x plus h all squared plus 4 times x plus h. Let me expand and simplify the f of x plus h so that it will be easier to work on later. So that is giving me 3 multiplying x squared plus 2hx plus h squared. And then we have plus 4x plus 4h. Expanding, going further, we have 3x squared plus 6hx plus 3h squared. Then plus 4x plus 4h. There's no way we can actually add and simplify, so we just leave it as it is. And then going further, we have to write up from first principle. We know that dy dx is equal to limits as h approaches 0 for the function f of x plus h minus f of x all on h. So at this moment, all that we need to do is to substitute for the function. So we have limit as h approaches 0 for f of x plus h is the lengthy expression here. So we have 3x squared plus 6hx plus 3h squared plus 4x plus 4h. That is f of x plus h. Minus into brackets, f of x is 3x squared plus 4x. Then all this must be divided by h. Now, we need to simplify before we substitute for h. So simplifying, let me do all that together. dy dx will be equal to limit as h approaches 0 for 3s squared minus 3s squared. So I've regrouped that. That is this and that. And then I equally have plus 6hx plus 3a squared plus 4x and then plus 4h. Then I have minus 4x. Minus 4x. So you bear with me that I've considered every expression there, all divided by h. Then I close my bracket. Now we'll be having 0 here. We have 4x and negative 4x. That will also give us 0. So we are left with limits as h approaches 0 for 6hx plus 3a squared. And then we also equally have plus 4h, all divided by h. Remember, this is gone. That is also gone. 4x and negative 4x. So we are left with 6hx, 3a squared, and then 4h. If you look at it carefully, still you cannot actually substitute for h. Therefore, we need to factorize out. So limits as h approaches 0 will be h out, because h is common to all of them, into bracket 6x plus 3h and then plus 4, all on h. So h can do away with the h there, and then we are left with limits as h approaches 0 for 6x plus 3h plus 4. Then at this stage, we can substitute for the value of h for 0. So we have 6x plus 3 times 0 plus 4, which leaves us a final answer of 6x plus 4. So it tells us that when we find from first principle the derivative of 3x squared plus 4x, we'll end up getting 6x plus 4. My students, or students in general, please make sure that you understand the concept of first principle, because look at this type of question. It is a question, a compulsory question for that year for 3 marks, for 6 marks. And therefore, if you don't have an idea of how to go about it, it means you are going to lose all the 6 marks for a compulsory question. So please practice as many work examples, and I believe you'll be fine working it on. Let us add more work examples to it so that you know how to go about situations like that. The next example I have here, we have f of x. Find from first principle the derivative of f of x equal to x plus 3 all squared. Remember, it was also a compulsory question, question number 2, in the year June 2016. Now, in going ahead solving such a question, we've been given that f of x is equal to x plus 3 all squared. Now we need to find our f of x plus h, and that is going to give us x plus h plus 3 all squared. Remember, wherever you see x in the original function, to find f of x plus h, you just substitute it with s plus h for x. Now, let us go ahead and expand our expression so that it will be easier for us to work on. When I consider f of x, which is given as x plus 3 all squared, when I expand, it gives me an answer of x squared plus 6x plus 9. That's the expansion for it. Now, if you want to know how it was done, you can just multiply it as x plus 3 multiplying x plus 3, and you get the answer for that. Now, again, coming to f of x plus h all squared, because it's so complicated, let me do it one after the other. So, x plus h plus 3 multiplying another x plus h plus 3. So each factor in the first bracket multiplies every factor in the second bracket. So in other words, we are going to get x multiplying x, that will give us x squared. X multiplying h will give us plus hx. Then we have plus 3x. Then we also multiply h by x, we get hx. Multiply h by h, we have plus h squared. H plus h multiplying 3 will get plus 3h. Then the last factor will be 3 multiplying x, that will give us plus 3x. 3 multiplying h, that will give us 3h. And then 3 multiplying 3, that will give us 9. Now, moving further, we have some like terms. So let's see, and then regroup the like terms and work it on. So x squared, hx is here, hx is there, will give us plus 2hx. Likewise, we have 3x having a counterpart 3x there, that will give us plus 6x. And then we'll have plus a squared, it doesn't have any counterpart. And then we have plus 9. So when you simplify that, this is what you are going to obtain. Again, if you want to check whether you are on course, let me use a yellow marker too. So hx, another hx gave us 2hx. Now we had 3x and 3x here. We had 6x. Then we also had to consider a squared had no counterpart, but we had 3h, so that one too has to come on board. And then we have 9, so we have left one out, and that is actually h, 3h and 3h. That will give us plus 6h. I believe it is well understood. So this way, what we obtain over there, I can rewrite it, and that gives us s squared plus h squared in order of magnitude, then plus I have 2hx plus 6x plus 6h and then plus 9. So this is the expansion for f of x plus h. That's the expansion for f of x plus h. So we are asked to use first principle. So going straight ahead from first principle, then we state dy dx will be equal to limit as h approaches 0 for the function f of x plus h minus f of x all on h. So remember, we are going to substitute. So limit as h approaches 0 for f of x plus h has been seen to be x squared plus a squared plus 2xh plus 6x plus 6h plus 9, then minus f of x, and f of x is x squared plus 6x plus 9. Then all this must be divided by h. Now remember, there are some of the terms in f of x plus h which is also in f of x. So those terms will give a 0. So without wasting my time, dy dx will be equal to, let me use a yellow marker to do away with such terms. So x squared and negative x squared will give a 0. Now we have positive 6x, negative 6x will give a 0. Positive 9, negative 9 will give a 0. So we are left with what? We are left with h squared. We are left with a squared. So limit as h approaches 0 for a squared, that is one thing we are left with, plus 2hx, we are left with that one as well. Then plus 6h, we are also left with 6h. So let's go back to check whether that is what we are left with. So that is what we are left with, all on h, all on h. Remember, we cannot substitute the value of h at the moment, so it means we have to go further and then factorize out. So that is giving us limits as h approaches 0 for h out into brackets, h plus 2x, then we have plus 6, all on h. Now the h, we do away with the h here, and that will be left with limits as h approaches 0 for h plus 2x plus 6. And therefore, since we done away with all discontinuities, then we can substitute for the value of h. So we have 0 plus 2x plus 6, and the final answer becomes 2x plus 6. So it tells us that the derivative of x plus 3 all squared is 2x minus 6. 2x minus 6. It's a very great privilege coming your way with this beginning for calculus. And I've started with differentiating from first principle. Please, if you've not subscribed to my channel, kindly subscribe, leave comments, and then like my video as well as share it for other people to also understand mathematics with ease. Thank you so much and have a nice day. God bless you.